I thought I'd start out by giving a little bit of a background to the gravitational wave detection, a bit of the history of it. As many of us know, gravitational waves came out of Einstein's 1950s, presented general theory of relativity. He actually, in 1916, came up with the concept of gravitational waves, and then in a paper he gave in 1918, he came up with what's called the quadrupole equation, which is a pretty good approximation to the power that would be produced by a gravitational wave generation system. Now, at the time, there was considerable skepticism as to whether or not gravitational waves actually existed. If they did, it was clear from the quadrupole equation that it would be a very, very weak signal that one would get, and the question was, would anything possibly produce that signal? People began to think a little bit about things like stars rotating around each other, double star systems, and in the laboratory, thinking about spinning rods or dumbbells and that kind of thing. The spinning rods or dumbbells, the rate at which you'd have to spin it would be such that you could not think of any kind of material that would hold the two ends of the dumbbells together. So that didn't seem like a reasonable way to go. As a matter of fact, that particular way to go stifled much of the early interest in the laboratory generation of gravitational waves. But nevertheless, there were a number of papers written, lots of them in the 50s and some in the 60s, showing what would happen if you had a binary system, particularly a neutron star binary system, and the kind of gravitational waves that you would generate. A fellow by the name of Joseph Weber thought that one might be able to sense these gravitational waves if you develop something like a bell that would be rung by the gravitational waves, and you would be able to hear the bell. This bell that he designed, called the Weber bar, was a big cylinder of aluminum. It's probably the first effort to develop a gravitational wave detector. It's from the Smithsonian Institute and has the first real way that you might detect it. His idea was that for the very low frequency gravitational waves, if you think about the star system, the neutron star system rotating, as I mentioned in an earlier talk, each time they rotate, they produce two gravitational waves. One rotation produces two gravitational waves. But still, the rotations periods are very short. Could be 10 seconds, maybe if they're going really, really fast, down to a fraction of a second, but that means you're getting very long wavelengths. That is a length, since gravitational waves move at the same speed as light, that means they go, wavelengths would be as long as light travels in a second. It would be 6,000 miles per second, so it's 6,000 mile long wavelength, or a 1 second periodicity of the gravitational wave, or a 2-second periodicity of the star system. Well, he set this all up in a laboratory in Malibu, California. Hughes aircraft supported him in this, and one of his students was Robert Forward. Robert Forward's name comes up frequently in this. This is, from my point of view, the way I got introduced to it, as he came out of the laboratory and gave a talk. Well, there was a great deal of, Weber was a hyper guy. He was skinny and ran back and forth, and he kept saying, I detected these gravitational waves. In other words, he will show me the evidence, and he'd show me, and say, no, that's noise. And so nothing really happened there. And then, as I mentioned before, Gilson Taylor actually made some indirect proof of gravitational wave generation by watching this double neutron star and the radio frequencies, watching it that way. Well, that focused the astrophysicist's attention on possible sources of gravitational radiation, and particularly Kip Thorne at Caltech and some others at MIT and throughout the world felt that, well, if you had some really massive things, such as black holes, and if they orbited one another, and if they lost energy through gravitational radiation and other losses, finally coalesced, you would have a big signal, gravitational wave signal, but a fairly low frequency. They convinced the National Science Foundation to produce what was called the Laser Interferometric Gravitational Wave Observatory. Now, the Weber bar was like a resonance chamber approach. That's one approach, and I'll talk about some others before I really get into this to show you thinking about this. But the LIGO and the advanced LIGO and the GEO 600 over in Europe, and Virgo, all of these based upon a fairly simple concept. When people talk about gravitational waves passing, they talk about a rubber ruler that contracts and stretches, actually due to the polarization change in this protein. That little change isn't very much. It's, for a kilometer or so, it's like a fraction of a proton. So, but you are directly looking at the effect of gravitation. And so that's a fairly simple thing to take. Now, it turned out, and this was probably in the late 1980s, some studies were made concerning the Big Bang and the microwave background and so forth, that there was also a high-frequency gravitational wave background. And Gryshak and Rudenko over in Russia and a number of people in Italy, a whole slew of them, developed theories, and the frequencies here were on the order of 10 gigahertz that would be naturally produced by the initiation of the universe. Well, that started focusing people's attention on high-frequency gravitational wave detectors. The technology, of course, is way different than the technology behind these other low-frequency ones. One of the people that was interested in it was Michael Cruz at Birmingham University, England, and we had dinner one night and we were talking about how he got his idea. He said, well, gravitational waves have such a low intensity, you need something like a feather to see how it moves. In like a very, very light breeze, you don't have a big weather event. You need something very light. And his idea was to develop a microwave circuit, a little loop, microwave loop, gravitational wave going through it would change something rather like polarization of the gravitational wave, probe. In any event, he and his graduate student, Richard Ingley, worked on this. I have shown, I think Monday, I showed some pictures of their laboratory and built it. The sensitivity, however, was not anywhere near predicted by the relic high-frequency gravitational wave theories. Another approach, like the Weber bar, only using resonance chambers, was developed by a Cinquenari and Yemi in Italy at INF in Genoa. And I saw their apparatus too. It's two balls about this size, roughly the wavelength you're looking for. The wavelength here is in the order of a few centimeters for the 10 gigahertz. And these small balls, one has a slightly different resonance than the other one. They sort of have a beat resonance together. A slight change, an infinitesimal change, the distance of a nucleus change in the size of the walls does indeed produce a signal. And so this was another way of doing it. They too had problems with sensitivity. It just wasn't sensitive enough to get the predicted relevant field. Okay, now, as I talked about in the last paper, I should be giving all the papers this morning. Yeah, in the last paper that I produced, I'll be talking a little bit about the Chinese. The Chinese, in the point of Fan Yu Li, said, well, there's another effect that we know. And this is a Gaussian Beam effect in which this paper, a very short paper, was done, I think, in 1962 or 63. He said, and they proved theoretically, and nobody's doubts it at all, fairly simple proof, that gravitational waves can be produced by electromagnetic waves under certain circumstances. Those circumstances being that their frequencies will be the same, but they have to be under a very strong static magnetic field. Okay, and the very last sentence of that paper says, and of course, the opposite can be done. That is, gravitational waves can produce electromagnetic waves. Okay, therein lies the seed that Fan Lee started. So he began to think about this. And another thing that came into it that was quite interesting is in Hong Kong University Institute of Technology had come up with the concept of what's called fractal membranes. These membranes are almost total reflectors for a specific polarization. And he thought, well, this might lead to some ability to separate out some background photons from the photons that were produced by gravitons. So this is really the basis of his whole effort. He has come up with 2 and now 3 kind of designs using this inverse approach. The first one was fairly straightforward. And I'm going to go to the slide here kind of to show you. This is a static magnetic field, and that's an important aspect of the important ingredient for the generation of photons from gravitons. These reflectors on each side of the fractal membranes, and he passes a field through that's coming into the screen, and under those circumstances, he can build up a standing wave of electromagnetic waves that are built up almost like a laser type thing. Now, that comes out, and if you put your detector out where he calls them perturbative photon flux, which is simply the photons produced by the gravitons, that detector is going to be overwhelmed by the electromagnetic field that has to pass through there in order, because you need an electromagnetic field at exactly the same frequency that you're looking for the high-frequency gravitational waves, and you need the static magnetic field, but you have to have that very strong beam going through there. So that means he can't put a detector right there. Now, the detector, the whole thing is a detector, but the microwave detector, is also the result of a electromagnetic beam coming through the very strong electromagnets. And then you need something, in here the perturbative photons are produced from the gravitons. The perturbative photons are of a particular polarization, so he puts these fractal membranes in here. They are kind of cup-shaped in the direction in which you are looking. They would represent like mirrors. You think of say a concave mirror in here. This concave mirror, then because it operates at exactly the polarization that they're looking for in the gravitational wave, brings the perturbative photon flux out. It turns out it goes both ways, and you put detectors out there. To show you the actual three-dimensional picture, here it is. In comes the high-frequency gravitational waves. Also, in comes a beam of electromagnetic power. In here, you have your very strong magnetic field, and the perturbative photons start joining up with the regular electromagnetic beam that's coming through here. They come up here and not shown here, but at this point it's a fractal membrane. Well, the fractal membrane takes advantage of the fact we know precisely what the polarization of the high-frequency gravitational waves are. It then picks those, this so-called perturbative photon flux, out in this direction, and then you go out in the symmetrical wave in this direction too. So you have a detector here and a detector here. The main calculations and theory and so forth behind this is entirely due to Fan Lee and another associate of his, Dr. Fang, here in Chongqing University in China. Here's the characteristics of this particular detector. It has a very strong magnetic field, 3 Tesla. As I said before, it has a 10 gigahertz The power of the Gaussian beam, or the beam that's going through there, the first one is about 10 watts. It's going into a waste. Just let me go back. The waste is in here. This is the beam essentially is waste of about 1/100th of a square meter. The quality factor of the open microwave cavity, which is here, is assumed to be 10 to the 11th, and the distance, to give you an idea, the distance here, E, is about 1 meter. So this is something that could fit into the length. And now, this is looking for relic gravitational waves. Okay, we put those in, and then you go through some calculations. This would be the amplitude of the gravitational wave. Now, the amplitude is given in the change. In other words, if you have this wave, so it's a meter stick, this is essentially the strain on that is in meters per meter. So this means that if you have a meter stick, the change in the actual length is 10 to the minus 24th meters. This begins to give you a feeling for why detection of these gravitational waves, be they high frequency or low frequency, are really different. These simply go through. This is the number of the perturbative photons, that is, the photons produced by the system, and then they are multiplied. They go back and forth, in this laser light thing, and then they come out over here, 5 times 10 to the 19th of these. As you suppose that the amplitude of the gravitational waves reduce, it goes down, down, down. These things dramatically drop. Here, you only have one that is produced. That's about the littlest you can have, about 4. I think it's in this area. You've just got a couple of them there. Because they resonate back and forth in this cavity, they then lead to about 5 times 10 to the 15th photons. This was shown simply as a showing that if you had almost negligible, you could still get some kind of amplification. But I don't think that's an interesting thing. Now, in order to measure this with a standard, perhaps quite sensitive microwave receiver, you need about 10 to the 5th of these perturbative photons. So this would give a fairly strong signal. A strong signal is really important in this business because you would like to really see the makeup of the relative gravitational waves. Just knowing that, yes, I can see them, or I detect them, of course that's good. That would be a breakthrough that you detect the gravitation. But if you want to do something about it, like you do with the microwave background, you'd like to get some fine structure and find out really what it's about. Is it frequency variation? What is its polarization shift? Blah, blah, blah. So, this is the essence of their idea. Now, there is another equivalent idea that they're working on now. Well, let me just go through this one, and then I'll tell you what if you have an open cavity with high quality factor and a Gaussian beam passing through it, high frequency gravitational waves can be could be detected in the gigahertz band. The perturbative photon flux requires an amplitude of 10 to the minus 26 or larger. Yeah. Oh, 5 minutes. 10 to 26 are larger. Unfortunately, you really, most of the theories, and at least in this case, where it's not the case in LIGO, unfortunately, in this case, you have certain ground rules for this required sensitivity. In LIGO, I don't want to get into that, but it looks like maybe once in 100 or 1,000 years they might get a signal. There they designed LIGO with the feeling that certainly you would have black holes coalescing in certain distances out in the universe, and everything would be okay. When you actually calculate it, you find out it's not as easy as that. But here they realize that they have to do something more because they've got to get down into this range. If they got down to 10 to the minus 28, that would be probably okay. But to do any real, be sure you're really catching anything happening here. So what so they are now trying to look for an increase in the Q, greater than 10-watt beam, stronger than 3 Tulsa magnet, and that kind of thing to build this. But there are other ways to do this. But they're working, there's quite a few in China working on this project. It's quite different than here in the United States. I'd say on the order of maybe 100 different scientists. That, of course, is small compared to what I have, probably 1,000 scientists involved in that program. But in any event, another one they're looking at, and let me go back to the other picture. Another one they're looking, no, maybe, yeah, they're looking at just this Gaussian beam here. None of the amplification with this cavity. And a strong electromagnetic beam, microwave beam of 10 gigahertz going through here. And then on each side, they're putting in something like a laser system so that they are amplifying these two branches. The magnetic field is along X and Y, the electromagnetic field and the high-frequency gravitational waves are along Z, and according to the theory, orthogonally outcomes in both directions. The microwaves, well, they're putting in here using fractal membranes because, again, they're taking advantage of the sensitivity to polarization and making little cavities here, essentially amplification chambers on each side, and then picking them up here. Under those circumstances, in theory, you can measure high-frequency gravitational waves down to 10 to the minus 32. And so they're starting to concentrate on this. Their plans, and I'll talk about that in my last talk, of actually building these things. Hopefully they'll have one built in about 3 to 4 years. Okay, that's essentially it. Okay, questions?
Have you ever thought of, I was looking at the box that you have there, the reflective surfaces. Have you ever thought of maybe trying to measure a Casimir type effect with the gravitational waves? Is there any
I think they have thought a little bit about that, but they tend to get tied up in some idea that what they have thought of is from this is a high temperature superconductor put in with reflective walls and so forth. But the Casimir, I don't think they have. But there's enough working on it that some of these ideas will probably surface. I'll mention this to them.